Okay, so let's talk about section 2.2, and title of this section is Venn diagrams and subsets. So these are the two things we're going to talk about today. And what I want to do is just start off by talking to you about Venn diagrams. And Venn diagrams are a very useful way for organizing information about sets in a pictorial manner. Okay, so using a picture. So I can start with something like this, with a box. We always start with a box when we're dealing with Venn diagrams. And the box consists of our universal set. So we put a little U down in the left-hand corner, and that represents that this box is showing our universal set. The universal set contains all of the elements of whatever it is that we're talking about. So we might be talking about, hair colors, possible hair colors. We might be talking about, the number of stars in the sky, or, the set can be as small or as large as you decide to make it, okay? And it doesn't have to do with numbers necessarily. Okay, so U is defined to be our universal set. Okay. And then within that universal set, we can talk about subsets, and we represent these subsets with circles. So, for instance, this right here could be my set A. And so over here, we're going to define A as a set that is existing within the universal set. Okay. Now, you can have other sets that exist in this in this universal set. For instance, if I was to draw, I could draw a set B, and I could draw a set B that isn't intersecting A. And if it wasn't intersecting A, then I would be showing a set that contains elements that are a part of the universal set, but aren't a part of A. If I wanted to show, something where a couple of sets were showing elements that they shared, then it would look something like this. Okay, so we're going to get more into Venn diagrams as we move on in this class, and today this is just a little bit of an introduction to this. Okay, and really what I'm concerned with today is that the universal set, that we can have sets within that, and those are subsets. And then there's another notation that I want you to understand, and that's this. If I have the universal set, and then I have some subset A here, I can talk about A complement, and A complement is, we use a prime. That's not a 1. It's like a hash mark that's up in the exponent there of the A. And you can either call it A naught, you can call it A prime, you can call it A complement. All of those things refer to the complement of A. And the complement of A is simply all of the elements that are in the universal set that aren't in A. So it's like, we have this, and then we have the universal set. And A complement is going to be everything that's on the outside of A. Okay? So just to define this, A prime, this is the complement. I'm running out of room there. That word says complement of set A. And this is the set of elements in U that are not in A. Okay? All right. Another way that we can, this is like writing it out in words, and another way that we can write a complement to show it mathematically using our set notation is to show it like this. We use our squiggle brackets, and then we could say this is X such that X is an element of U, and X would be one of the whatever elements we're talking about. So we have an element such that the element is an element of U, and it's not an element of A. So that is set notation for A complement. Okay. All right, let's do an example so you can see more clearly what I'm talking about. So let's say that I have a universal set that has the elements of these numbers right here, 1 through 10. Okay. And I'm going to go ahead and let set A be the set that has the elements of 2, 4, 6, and 8. And I'm going to let set B be the set that has the elements of 1, 5, 7, and 10. Okay, so what I want to do is I want to find, first of all, let's go ahead and find A naught, or A complement here. Okay, so remember, A complement, excuse me, A complement is all of the elements that are a part of our universal set that are not a part of A. Okay, so if you notice here, the elements we have in A, 2, 4, 6, and 8, the elements that aren't in A but are in U, we have 1, we have 3, 5, 7, and then also 9 and 10. Okay. In the second one here, why don't we identify B complement? And B complement is going to look like we have the 1, so 1 is an element. We want everything that's not. So we have 2, 3, 4. We have 6, 8, and 9. Okay, so just the idea of complement is relatively basic. Okay, next thing I want to talk about is subsets. And let's talk about define it first. So we have the subset of a set. And we say that set A is a subset of set B if every element of A is also an element of B. Okay? And in symbols, that looks like this. A is a subset of B. Now, based on this definition, set A is a subset of B if every element of A is also an element of B. These could actually be the same set based on how this is defined. They don't have to be subset, for A to be a subset of B, but they could be. Okay, that's in distinction to something like a proper subset. So the definition of a proper subset is something that is a subset, but specifically A and B are not equal. Okay, so a proper subset, this is when we say set A is a proper subset of set B if A is a subset of B and A is not equal to B. Okay, so the way that these are different is simply, a subset can actually be the same set. A and B can actually be equivalent, or excuse me, A and B can be equal. When you're talking about a proper subset, they can't be. And then it's just a definition thing. And the notation here is we would say A, is a subset of B. That's not a C right there. It's like a sideways U. It just looks like this subset notation, but without the bar underneath it. Okay, so that's our proper subset notation. Okay. So let's just do a couple of examples here to help make this make sense. So let's determine whether we want to use our proper subset notation or just our basic subset notation, both, or neither to answer the following questions. Okay. All right, so as an example, let's say that I'm looking at red, blue, and yellow as some set. And I want to know how that relates to yellow, blue, and red. Okay, well, if we think of this as like our set A and this is like our set B, they're actually the exact same set. They contain the exact same elements. The fact that they're not listed in the same order doesn't matter. The elements are the same. So it definitely is a subset, but it's not a proper subset because these two are actually equal to each other. Okay, so it's not both and it's not neither. It is definitely, this is a subset of that. Okay. Let's take a look at this example here. Let's say I have the set containing the days of the week, and this set contains these days, Monday, Wednesday, Thursday, and we'll make that a Saturday. Okay, so if we look at this set in comparison to this set, we can see that this has Monday, Tuesday, Wednesday, Thursday, and Saturday or Sunday, whatever you want to make that. Monday, Wednesday, Thursday here, and Saturday. This one has a Tuesday, this one doesn't. And we're always reading this from left to right. So I'm asking, is this a subset of this? And no, it's not, because this thing has, it has a Tuesday in it. This doesn't have a Tuesday. So not only is it not a subset, it's also not a proper subset. Okay, so this one's actually neither. Okay, and let's try one more here. Let's say that I have this right here, the set containing the numbers 1, 2, and 3, and the set containing 1, 2, 3, and 4. All right, so if you can see, this set contains all of the elements of this set, but they're not equal. So, oh, my phone's ringing. What do I do about that? I think I'm going to ignore it. So this contains, I don't know how to make it shut up, you guys. I'm sorry. Make it go away. Okay. 1, 2, and 3 these elements are definitely a part of this set, but this is not equal. Okay, so it is both a regular set, subset, but it's also a proper subset, because remember the definition of proper subset was that it is a subset, but it's not equal to. Okay, so this one's actually both. All right. Okay, next topic here. Let's do another example. Let's say that we have a universal set that contains these elements, A, B, C, D, E, F, and G. And then I'm going to give us some subsets here. I'm going to give us the subset A equaling A and E, and B equaling A, B, E, F, and G, C equaling B, F, and G, and D equaling D and E. Okay? All right, so let's ask ourselves a few things here. Let's ask if C is a subset of U. And basically, we're going to put a question mark here. Here's a statement, and let's identify if these are true or false. Okay? All right, so let's take a look. C has these elements, B, F, and G, and U has those elements as well, and they are not equal to each other. So this definitely is a proper subset. So that is true. Okay? If we take a look at something like D is D a subset of A? So if we look at D, and then we look at A, these are D is not a subset of A because it contains an element that A does not contain. So this would be false. Okay. And then this third one here that I want to consider is this. Is the empty set a subset of D? And you know, this is something I haven't mentioned yet, but the empty set is actually a subset of all sets. And so we would say this is true here, and this leads us into a discussion of, you know, how many subsets do we have for each of these, and I think we should analyze it. So let's just take a look at, for instance, the subsets of D. Okay, and let's just list all of them. So we're looking at D here. D has the elements D and E. And if I want to list all the possible subsets here, I could say the empty set is a subset. I also have the set containing just the element D, so that's definitely a subset. I have the set containing the element E, and then I have the set containing both D and E. Okay, so you can see that when I have a set that has two elements, I end up with 4 subsets. Okay. All right, well, let's analyze C. C has 3 elements. Okay, so if we look at B, F, and G, then if we want to list out all of the subsets of this, we know we have the empty set, and then we have the set containing the element B, and the set containing the element F, set containing the element G, and then I can start to do subsets of C that have more than one element. So we could do B and F together. We could do a set having B and G together. We can do a set having F and G together. B and F, B and G, F and G. We can also do, that's it for sets of 2, but then we have the set containing all 3 of them. Okay, so here if we notice that we have 3 elements, and then we end up with 1, 2, 3, 4, 5, 6, 7, 8 subsets. Okay, so there's actually a pattern here, and we should just draw out a little diagram so that we can analyze this pattern. So in the top row here, let's talk about the number of elements that are in any particular set. And then let's take a look at the number of subsets here. And I guess we've really only analyzed something containing 2 elements and something containing 3 elements. This ended up with 4 subsets, and this ended up with 8 subsets. Okay, why don't we go ahead and actually analyze this situation as well, so that we can fill in our chart. So I'm just going to give us an example set here. Let's say I got the set A that contains, I just want one element. Let me just give it the number 5. Okay. Okay, so the subsets here are the empty set and the set 5. So there's actually 2 subsets there. Okay. Now we could analyze something that has 4 elements in it and count out all those subsets, but let's see if we can get the pattern here. And there is a pattern. If you notice here, the number of subsets, this is in a base of 2. This is 2 to the first power. This is 2 to the second power, and this is 2 to the third power. So, you know, I can look at this relationship here: 2 to the first, 2 to the second, and 2 to the third. And if you notice, these exponents actually match the number of elements that I have. Okay, so that actually becomes a formula for us, and that formula is just 2 to the n. So let's write it out so you have it in your notes. So the number of subsets, this is the number of, the number of subsets of a set with n elements is 2 to the n. Okay, and so if we're saying this is in a generic form right here, if we're saying, we have one element, there's going to be two subsets. That's 2 to the first. If we have two elements, it's 2 to the second. 3 elements, 2 to the third. It's 2 to the n when we're talking about n elements. Okay. Now, if we were to look at the number of proper subsets, that'd actually just be 2 to the n minus 1. And the reason for that is, if you take a look at this, remember that a proper subset is defined to be a subset except for the fact that it can't be equal to the original set. So all of these are proper subsets of BFG except for this one. This one is not a proper subset. This one, yes, is not a proper subset because these two are actually equal to each other. And that's going to be true of all, when you're looking at all of these situations. So the number of proper subsets is always going to be 2 to the n minus the one that it actually matches. And so let's write that out. Okay, so the number of proper subsets, this is going to be the number of proper subsets of n elements is 2 to the n and then minus 1. Okay. All right, so that's not really rocket science. I mean, if I were to just give you some set A here that had a few elements in it, let's just give it 4 elements. So this is an n equaling 4, and that's because I have 4 elements in there. And let's say that I wanted to know, the number of subsets of A. Number of subsets of A is going to be 2 to the n, the way that we have it defined, right here, right? And so our n here is 4, so this is going to be 2 to the 4, which is 16. Okay, and if we wanted to then know the number of proper subsets is going to be 2 to the n minus 1, which is 2 to the 4 minus 1, which is 16 minus 1, or 15. Okay. All right, so that should give you enough info to go and do your homework. Let me know if you have questions.